So we're on to module 20D. I will warn you up front, this is a longer module, okay? It's just flat out going to be a longer video. Feel free to pause in the middle, find a good stopping point, or just prepare because there's a lot of material, a lot of content in this, and I just can't figure out a better way to split it up. So this is going to be a longer video. I apologize up front. In this video, I'm going to first introduce the differences between galvanic or voltaic cells, those words are interchangeable, and electrolytic or electrolysis, and then, which means basically voltaic galvanic is spontaneous reactions, whereas electrolysis or electrolytic cells are non-spontaneous processes. I'm going to explain the difference between these with some examples, and then I'm going to really delve into voltaic and or galvanic cells. So just as a general overview, again, as a reminder, what is electrochemistry? Electrochemistry is where we're studying that relationship between some kind of chemical reaction and the electrical energy that it either produces or it uses up. So either electrical energy is being consumed or being produced within a chemical reaction. Just as a general, just flat statement so that everyone is clear on this, all electrochemical reactions are redox reactions. Electrons are being transferred from one species to another. So all electrochemical reactions do involve redox. We may have a chemical reaction that then causes another redox reaction to happen. We may undergo a redox reaction, which causes a regular chemical reaction to happen. But if redox is happening, the redox portion of it is an electrochemical reaction. We have two kinds of electrochemical cells, galvanic, also known as voltaic, and then electrolytic, which are also known as electrolysis. The word galvanic and voltaic is completely interchangeable. They mean the exact same thing. They are just two different words for the same thing. And I'm going to zoom in on here. I'll zoom back out and explain these pictures in a minute. But I'm going to zoom in here so we can write on here. So two kinds of electrochemical cells. Galvanic and voltaic cells are spontaneous process. So you have a spontaneous redox reaction used to generate electrical energy. i.e., a battery. Think about a battery in your phone, a battery on your computer, a battery in a TV remote. What's happening inside that battery is a chemical reaction that is generating electricity that we're then able to harness, and it runs whatever device we want. When we are talking about this, remember spontaneous, we've already covered thermal chemistry, so we've talked about Gibbs free energy a lot. We know a spontaneous process, delta G, is less than 0. We know that our equilibrium is greater than 1. Our equilibrium constant, our K value, would be greater than 1. The reaction is proceeding towards the product side. It's going to proceed in the way it's written. In this chapter, we're also going to talk about cell potential, the overall potential energy of the reaction of the system itself. And we write E naught of the cell to represent your standard cell potential. And your standard cell potential will be greater than 0 or a positive value for voltaic and or galvanic cells. Again, voltaic and galvanic are completely interchangeable words. They mean the same thing. Electrolytic cells, which is also, the process itself is also known as electrolysis, is a non-spontaneous process. In this case, electrical energy is used to drive a non-spontaneous reaction. Example, your cell phone battery. You've used your phone all day long. The battery is now really low. You plug it in. It's now charging your battery. The battery does not charge on its own, right? It's not a spontaneous process. The battery doesn't just miraculously have charge. Instead, we plug it in. We use electricity to force the battery to charge. A non-spontaneous process. Because it is non-spontaneous, delta G will be greater than 0. 0 is less than K is less than 1. And your cell potential is less than 0 or a negative value. So now that we've got that note down, let's look at a couple examples here. One is electrolysis. Electrolysis is a way of splitting apart different species of a system. So here in the electrolysis, so again, this is going here, okay? I have these pictures a little bit backwards and I apologize for that. This is going here. Let's first talk about electrolysis though, and then we're going to leave electrolysis to more at the end of the chapter. But in the electrolysis of a pure molten salt, what does molten mean? Molten means melted. In this reaction, what I have here is completely melted sodium chloride. What I'm doing is I am splitting apart that molten salt. I see that I've got Cl minus going here and forming Cl2, and a plus here forming sodium metal. So in the electrolysis of pure molten salt, the anion in this case is oxidized and the cation in this case is reduced. It does not always mean that the anion and cation are doing this, but we see what's happening here. The chlorine is going from Cl minus to Cl2 gas. So two chlorines are losing electrons. Remember, losing electrons is oxidation. And I have a sodium going to sodium solid. It's gaining an electron. It needs one electron to do it. I know you can't really see that electron that I wrote in there. The balanced reaction is showing two sodiums because the chloride ion is giving up two electrons. So I've got to have two electrons reacting with two sodiums to form two sodium ions to form two sodium metals. This is not a spontaneous process, right? Even if I melt table salt, it's not going to randomly form back to chlorine gas and sodium metal, but I can force it to through electrolysis. Same thing, I can electrolyze water. I can take a beaker of water and hook a battery up to it. And I can form hydrogen gas and oxygen gas from the water itself. Because again, water, H2O, hydrogen is +1, oxygen is -2. I can remove those electrons from the oxygen, give them to the hydrogen. So if oxygen is losing electrons, oxidation is loss, the oxygen is being oxidized, and the hydrogen is gaining those electrons. Hydrogen is being reduced. Hydrogen is forming H2 gas. In the picture down here, a spontaneous redox reaction is zinc plus copper ions. In this picture here, I have a solution of copper sulfate. Copper sulfate has copper ions, copper 2+ ions, and sulfate ions floating around. The sulfate is your spectator. I put a strip of zinc in here, and what I see is those zinc atoms are going, the zinc atoms, so that's pure zinc in here, right? Your zinc strip here. The zinc is going to give up electrons to that copper. Now, the zinc has lost those electrons and it enters the solution as zinc ion, zinc 2+, and the copper is being reduced to a copper atom, as pictured here. This is a redox reaction. The zinc is losing electrons, so zinc is being oxidized. The copper is gaining electrons, so copper is being reduced. This is a spontaneous process. If I put zinc metal into copper, zinc will readily give up its electrons to reduce the copper. And it's hard to see in the picture here, but we see the color of the solution is actually getting lighter as well. That's because there's less and less copper in solution. The zinc is not colored. Copper is. So let's look at an overview here. In both types of cells, oxidation occurs at the anode and reduction occurs at the cathode. You have to keep that together. Some people remember it as, what do they call them? I never remember it because I remember it as anode oxidation. I put my vowels together. And cathode reduction, I put my consonants together. Some people remember red cat for reduction cathode and anox for anode oxidation. I don't know how else people remember them. Like I said, I put my vowels together, my consonants together. That's how I always memorized it. But I know that a lot of students remember red cat and anox. You can remember that as well, whichever makes it easier for you. But you have to remember oxidation is the anode always. No exceptions. It does not matter if we're talking about a voltaic cell or galvanic cell. Oxidation is at your anode. Reduction is at your cathode always. It does not matter what type of cell we're looking at. If you are at the cathode, the species is being reduced. The other thing is that the anions always migrate toward the anode, and the cations always migrate towards the cathode. Electrons always travel anode to cathode. I remember that because I think about the alphabet going A to C. So this picture down here, there's difluorine. It's her Twitter handle. She puts out some really nice graphics that can be fun, but also really help explain to students what's going on here. And I really like her graphic here because to me, visualizing it can help a lot on what's going on. In my anode, I've got zinc. I've got a zinc piece of zinc metal here, okay? This is basically kind of explaining that copper system we just talked about where we had here where I had the copper solution and the zinc. What if I split those up into two pieces? That's what's happening in electrochemical reaction. I'm splitting these up into two pieces. So again, difluorine, definitely check out their page. Really, really like their graphics. I think they do a great job with them. But I really like this one for electrochemistry because for me, it really helped me see what was happening. At the anode, we've got my zinc being oxidized, meaning it is losing electrons. I've got my zinc strip here. This is just a pure piece of zinc metal. And I can see the electrons being lost and my little guy falling into solution. Zinc is going from zinc solid to zinc 2 plus 2 electrons. Where are those electrons going though? The electrons are not staying in solution. The electrons are traveling through a circuit. I am completing a circuit here, okay? The electrons are traveling from the anode to the cathode, always. As the electrons travel to my cathode, on this side, I've got my little copper 2 plus, and she's gaining those electrons. So copper 2 plus gaining the 2 electrons to form copper solid. If I run the system long enough, the zinc would eventually run out. The copper would then eventually be full over here. I'd pull all the copper out of solution. In solution here, I have zinc 2 plus ions. In solution here, I have copper 2 plus ions. I also have that zinc strip and that copper strip. It is completing a circuit, okay? So my electrons, my zinc metal is losing electrons, adding more zinc into my solution. The electrons travel through, they light up the light bulb when they do so because I'm completing my circuit, and they travel over to my copper where my copper is being reduced. The thing is, we have to have a net balance of charge here, and that's what's occurring here in the middle, what we call our salt bridge. The salt bridge here, and I just drew over that by accident, is for charge balance. As my zinc is being oxidized, I am losing more and more electrons. This solution is going to get a net positive charge. At my cathode, I'm reducing things. I'm gaining electrons, so I'm taking copper 2 plus and giving it electrons, going to copper solid. Overall, this is going to have a net negative charge. To keep the system and the circuit going, I have a salt bridge that connects these two pieces. That's why batteries are split into different cells, right? Different pieces of the reaction that I separate, and then I can harness the power off of them. I see here a little negative charged chlorine traveling to kill that net positive charge, to neutralize out the net positive charge. Here, my little sodium, my little positive, going to cancel out that net negative charge. So the salt bridge just overall keeps the overall the electrical neutrality of your system. We'll talk more about that. We'll start drawing these, all of that, etc. But remember, again, a lot of students really like remembering red cat and anox. That's fine with me. I don't care how you remember it. But reduction, cathode, oxidation, anode, always. And electrons always travel anode to cathode. Follow your alphabet. So again, a voltaic cell, I explained a little bit in the picture, but what's happening here is we are splitting apart the two reactions. We're splitting up the reduction reaction from your oxidation reaction. We're connecting them by a salt bridge to keep our electrical neutrality going, and we're completing our circuit and harnessing the energy off of it. So here we see another system. I've got zinc, my zinc plus copper again, but in this time, instead of using people, I'm using the actual species, okay? In here, I've got a beaker that has zinc nitrate in it. Zinc nitrate, nitrate is just a spectator ion. That means I have zinc ions, zinc is 2+, and nitrate ions floating around. I don't care about the nitrate ions, but I can't just measure out zinc ions. I can't just buy a bottle of zinc ions. I have to buy a bottle of zinc salt. In this side, I've got copper ions, and it is copper 2+, nitrate, and nitrate ions floating around. And yes, I've got millions of those, so I'm not going to write, like, I'm not going to sit here and fit in my beaker 2 nitrates for each one. It doesn't matter. I'm using my salt bridge to keep my electrical neutrality going. And I see, then I've got my zinc strip here, my copper strip here. Okay, so the anode is where the species is being oxidized, always. The cathode is where the species is being reduced, always. And electrons are traveling from anode to cathode, always. What's happening at my anode is that the zinc metal in here is losing the electrons. The electrons are traveling up this metal strip through the circuit, lighting up my light bulb, and then eventually over to my cathode. Zinc is entering the solution as zinc 2+. On my cathode side, I already have some copper 2+ in the solution. I need to keep this overall solution together. That's how an electrochemical cell works. But the electrons are traveling down. They're finding that copper 2+ in solution and reducing it as copper solid. Again, these are voltaic or galvanic cells, which means that it's a spontaneous process. Which cell does what? In both types of cells, meaning by both types, I mean voltaic and electrolytic. Voltaic, again, also means galvanic. But when I say both types, I mean voltaic and electrolytic, or galvanic and electrolytic. Oxidation is at the anode, reduction is at your cathode. That never changes. What changes is what's at which species is at what position. But oxidation is always the anode, reduction is always the cathode, no exceptions. Again, the anions migrate towards the anode, the cations migrate towards the cathode. A's together, C's together. And I think I forgot to write that on here, I'm sorry. Anions migrate. Spelling is hard. Towards anode. Cations migrate towards your cathode. The way I remember, and then they each have a sign, a positive, negative sign associated with them. We are going to have to remember what sign is what, okay? And they differ if it's, this is the one thing that does differ if it's electrolytic or voltaic. In electrolytic cells, your cathode will be a negative charge, your anode will be positive charge. But in voltaic or galvanic cells, your cathode has a positive charge to it, your anode is a negative charge species. This you have to remember. And so the way I remember it is by creating this little chart. I follow the alphabet, A to C, E to V, and then I put a positive in the top corner, and I know my positives go on a diagonal. And my negatives go on the opposite diagonal. You do have to remember this. And part of it can just come from practice, but if you can remember the sign of the electrode, positives on the main diagonal, you should be able to get it correct. This, again, we're going to practice voltaic, but we do have to recognize this is the one thing that will differ between the two systems, is what we give it, what we assign for its potential, whether it be a positive or negative potential at that point. And that does change between electrolytic and voltaic cells. So voltaic cells, again, they're also called galvanic cells. The name's completely interchangeable. Let's talk about what happens when solid zinc is placed in an aqueous copper sulfate solution. I've got here a copper sulfate solution. Here is a zinc strip. I put this in here and I see what's happening here is that the zinc is slowly losing its electrons, forming zinc 2+. Excuse me. And those electrons are going to a copper 2+ species and reducing it to copper solid. If I let this happen over time, I've got this beaker over time, what I'm going to find I would still have my zinc strip, but it would be coated with copper. I could then take that copper metal out and weigh it. And if I looked at that zinc metal, the zinc would no longer look. It would be partially eaten away. It would not be what it originally started as. It would be partially eaten away. Some of the zinc would eventually just disappear or appear to disappear. It's not really that it's disappearing. It's going into solution as zinc 2 plus, and then the copper solid is forming out of it. So why is this happening? No, there's reasons why, and we're going to talk about why. We're going to talk about how to predict it as well. But first, let's write the two half reactions and the balanced redox reaction, what's actually happening. I know that zinc is being oxidized. I can see that here in the diagram. The zinc is going from a +2 state, or from a 0 state here to a +2 state here. The copper is going from copper 2 plus into copper solid. So the zinc is being reduced. Zinc is being oxidized while copper is being reduced. Oxidized would be zinc. Zinc solid is going to zinc 2 plus 2 electrons. The reduction reaction is copper 2 plus aqueous gaining 2 electrons and forming copper solid. So what is my overall reaction here? Overall, I add these two things together, right? And when I add these together, I get zinc solid plus copper 2 plus gives me zinc 2 plus copper solid. Why didn't I write my electrons? Well, they're on opposite sides of the reaction, right? Which means they cancel out. They are being transferred. They are there, but I'm not going to emphasize it because they're being canceled out on each side of the reaction. So the overall reaction here, the overall redox reaction is zinc solid plus copper 2 plus, giving me zinc 2 plus copper solid. But that is your net ionic reaction. If I wanted to write the molecular reaction, because that's usually what we're going to deal with in the real world, I would write zinc solid plus copper sulfate gives me zinc sulfate plus copper solid. Now it just looks like a single displacement reaction. But I know the truth, right? I know it's really a redox reaction. So one thing I really want to re-emphasize about voltaic cells is that this is a spontaneous reaction, meaning that it's going to happen without any outside source, any outside assistance. It's just going to happen the moment the chemicals are mixed. In the example we just looked at, which is pictured here as well, as soon as that zinc solid strip, so that strip of zinc is placed into the copper sulfate solution, it begins reacting. Zinc begins, immediately starts getting oxidized, meaning the zinc is immediately going from solid zinc form or phase to zinc 2 plus in solution. So it's immediately losing electrons. The copper in solution the copper ions immediately start accepting those electrons and reducing down to copper metal. And we can see in the picture here, the solution gets lighter and lighter because there's less copper in solution. Zinc isn't absorbing color. Zinc, if you think about the electron configuration of zinc, it's D10, 3D10 specifically for its valence electrons. And so it's got full filled shell. We'll learn more about that in inorganic chemistry, but it's not going to absorb color because it's got a full filled shell. There's nowhere for the electrons to really advance to or excite to. Voltaic cells can be generated by physically separating the two half reactions and connecting the two half reactions with an external wire, which is what I pictured or what I showed pictured in that cartoon and also in the diagram before, kind of showing the anode versus the cathode. I physically separated out the two pieces of the reaction. I do this so that I can actually I can harness the electricity coming off of that reaction. It's not just lost to like heat of reaction. And so draw the galvanic cell that's formed when a standard copper 2 plus copper half cell is electrically connected to a standard zinc 2 plus zinc half cell. That's what we have pictured above, but let's go ahead and just give ourselves some space and draw it as well. Let's say we have two different beakers, okay? We've got 1 and 2. Each beaker is going to have some kind of electrode in it, some kind of solution in it, and these are going to be connected by an external wire and a salt bridge. Let's go ahead and label everything we got. So this here is my salt bridge. Again, the salt bridge is there to keep electrical neutrality within your system. It's to balance out so we don't get an overall positive charge or negative charge on either side of our cells. It's to keep everything equal. It's connected by a voltmeter. And in the case of zinc and copper, this would be a zinc electrode, and I would have zinc 2 plus in solution. This would be a copper electrode, and I would have copper 2 plus in solution. This is zinc sulfate. This is copper sulfate, because I said let's use a sulfate solution. Or maybe I didn't. It doesn't matter as long I just want to pick a spectator that's not going to be involved in reaction. So sulfates are good. Nitrates are really common to use. Nitrates are really good at conducting electrical current without reacting themselves. So nitrate isn't going to do anything. Let's see. What do we got going? What else do I need to label here? This is my anode. This is my cathode. The anode, a galvanic or voltaic cell, will have a negative charge to it. The cathode will have a positive charge. So some people remember cation plus sign, that's one way to think about it. But again, they swap sides when you get to electrolysis. The other way to remember it is that little chart that I taught you guys, I'm doing anode, cathode, electrolytic, voltaic or galvanic, either way works, plus, plus, minus, minus, that little chart. Our electrons always travel from the cathode to the anode. So the electrons are traveling from the zinc to the copper. The salt bridge is going to be made up of anything that's not going to react, but we like to use common ions. So in this case, since I'm using sulfates, I'm going to go ahead and use a sulfate salt for my salt bridge, and I'm just going to label it as sodium sulfate. I want to pick some kind of species that's just going to behave as a spectator and not actually react with the system at all. So on my anode side, again, anode is oxidation. I've got zinc being oxidized. So zinc solid is being reduced to zinc 2 plus and 2 electrons. At my cathode, I've got copper 2 plus ions gaining those 2 electrons and being reduced to copper solid. Overall, all of this is going on in this system. I've just split the reaction into 2 pieces, so it's not happening in one beaker now, as was pictured here. It's not happening in one single beaker. It's happening across 2 beakers because now I can harness that energy. And to complete the reaction, I'm going to write these down here. I've got my zinc. I've got my copper. And I can look up what we call the cell potential for each reaction. The standard cell potential for zinc solid going to zinc 2 plus and 2 electrons is positive 0.76 volts. The cell potential for copper 2 plus gaining 2 electrons forming copper solid is positive 0.34 volts. When I add up the overall of these reactions, I'm left with zinc solid I apologize, I forgot I still had that on. Zinc solid plus copper 2 plus, giving me zinc 2 plus copper solid. And the overall cell potential here, I just add those two numbers together, is 1.10 volts. So if I was to complete this reaction, if everything was perfect, if the concentrations of the zinc and copper were identical, we'll talk more about that in this module as well, excuse me, I would be able to harness a cell potential off of this of 1.10 volts. So that's the voltage of the battery. So, two half reactions connected with an external wire. As a result, the electrons would transfer through the external wire, producing an electrical current. If I left them in one beaker, I would not be able to harness that energy. Because I've separated them out between two beakers, I can actually use that energy and produce that electrical current that I can then use for something else. The cells themselves. The previous example illustrates several things. The first is that each half cell consists of the oxidized form of a substance in physical contact with the reduced form. What I noticed there when I drew these, here, I've got the oxidized form of zinc in physical contact with my reduced form. Same for copper. I've got the oxidized form in physical contact with my reduced form. Even though zinc is being oxidized, copper is being reduced in the system, I still have the other species present. The two half cells were physically separated and connected by an external wire and a salt bridge. So completely physically separated but connected by something that's not allowing the chemicals to mix, just the current. The solutions were connected by that salt bridge, which is, or also you could use a porous partition, something that's going to allow those spectator ions to travel. The salt bridge is, it's preventing solutions from mixing. It's allowing the reaction to occur, but preventing the solution from mixing. It remains the it keeps constant that maintains the electroneutrality of your system, but it also completes your electrical circuit. We need to be able to complete the circuit. By using the salt bridge, we're able to, again, if we think back to that cartoon that I showed in the beginning, we're able to keep that transfer of electrons balanced because the spectator ions of the salt bridge are traveling opposite of the electrons to keep the electroneutrality of the solution. But it's also allowing the solutions to react by letting the electrons transfer without letting the reaction itself, without letting the chemicals just mix and have all of that, the heat generated in the reaction lost as heat. Instead, we're able to harness that electrical energy. The electrodes are in each half cell as well. So the electrode was that solid metal piece I was talking about for zinc and copper. It's a solid metal when the metal is involved in a reaction. So like in this examples we used was zinc or copper. If I am oxidizing zinc metal or reducing copper to copper metal state, I'm going to use the metal that's actually involved in the reaction. Sometimes I'm not using that though. Sometimes I'm going to reduce things like iron, what if I'm going between iron 2 plus and iron 3 plus? If I'm oxidizing it that way or reducing iron 3 plus to iron 2 plus, then I'm not going to use an iron wire in there. Instead, I would use some kind of inert material like a platinum wire mesh or a piece of graphite. And I use that when the reactants are ions in the solution. And we will see examples of that as well. So how do we prepare these cells? Excuse me. How do we represent them? We use a shorthand. We're going to use a shorthand method to represent what is actually happening in these cells. And then we're going to connect the shorthand to the diagram, to the reactions, so we can talk fully about everything going on. So I want to write the shorthand or cell notation for the galvanic cell that is formed when a standard copper 2 plus copper half cell is electrically connected to a standard zinc 2 plus zinc half cell. We already saw what that looked like, right? We already drew the diagram. We already drew the reactions. We know what it looks like. How am I going to represent that without drawing out that whole system every time? I'm going to use the shorthand where I write the anode. Oops. Anode. Single line. The anode electrolyte, and I will explain what all of these things mean in a sec. Double line. Cathode electrolyte. Single line, and cathode. The anode is the physical piece, so that piece of metal or that inert material that is at the anode itself. It is your physical solid phase species. Cathode is that physical solid phase species at the cathode. So in the example we just did, that would be our zinc metal and our copper metal. The electrolyte is the species that's in solution. The solution is what's allowing those electrons to transfer. Okay, the electrons are able to travel through that solution and then eventually through the anode and cathode to the other side of the system. This line here is a phase boundary. We find that we're going to use that when we're flipping between solid to liquid phase, liquid to gas phase, or solid to gas phase. If we are separating out two different phases, physical phases, we're going to use a single line. The double line here represents your salt bridge. And that separates the anode from the cathode. This is your other phase boundary on the cathode side. So let's write what this will look like for the zinc example. In the example we had at zinc, we know that zinc was our anode, and we had a piece of zinc metal in there, and we know we had zinc 2 plus present. Zinc 2 plus only exists in aqueous phase. So I'm going to write these, but I'm going to put a phase boundary between the two because they are in different phases. That's all I have present in zinc. I could use zinc sulfate, yes, but the sulfate is a spectator. I am only writing down what's actually involved in the reactions themselves. Spectator ions are not involved in the reactions. I'm going to write my bridge, my salt bridge, and then what do I have on the other side? On the cathode side, I had copper 2 plus, aqueous, phase boundary, and copper solid metal. Note, I did not write any concentrations here. If you do not write concentrations, you are implying that you have a 1 molar solution. 1 molar is standard, the standard conditions for an aqueous solution. So no concentration. You are implying 1 molar. You are always welcome to write the molarity in here, even if it is 1 molar, but if it's not 1 molar, you have to write it. And you would just do that by writing a parenthesis and the concentration inside of there, next to the electrolyte species. Again, if it is not 1 molar, you have to write the value in, because by not writing it, we are implying that it is 1 molar. So let's work some examples. Draw the galvanic cell that is formed when a standard copper to copper 2 plus half cell is electrically connected to a standard Fe2 plus Fe3 plus half cell. Write the electrochemical shorthand for this cell. I'm going to do that, and I'm also going to write the overall cell reaction so that we can start to see where these are coming from. Let's first work on drawing the galvanic cell. When I say draw the galvanic cell that is formed or produced, that means draw your beakers and tell me what's where. So let's go ahead and draw our beakers. I've got my 2 beakers. I know this is my anode. Oops. I know this is my cathode. I'm always going to write the anode on the left, the cathode on the right. I know that I have copper 2 plus, and iron 2 plus, iron 3 plus. Because I have copper 2 plus, I will have a copper wire, or piece of copper metal. And because I'm using iron 2 plus, iron 3 plus, there's no metal in there. I'm not going to use iron metal. I don't want to reduce this down to iron, solid iron, or oxidize from solid iron. So I'm going to have to use some kind of inert material. So I'm going to pick a platinum wire. I have not yet taught you how to identify which one is going to go on which side. So I'm going to have to tell you right now, just to trust me, but the copper is going to go on my anode side, and on the cathode is going to be my platinum wire. So this is my copper, this is my platinum, And that means in solution, I have copper 2 plus, I have iron 2 plus, and I have iron 3 plus. Not done though, right? I still gotta label a few things. I'm missing my salt bridge. The salt bridge is what's connecting these two pieces. So that's my salt bridge. Let's write that in different colors so we can actually see it. So salt bridge. And because I didn't give myself very much room here, move this down. We do have to have our external wire representing it by our voltmeters so we can actually connect it electrically. My electrons will always travel from my anode to my cathode. And because I have a voltaic cell, my anode will have a negative charge and my cathode will have a positive charge. Let's see, what else am I missing? Half reactions. What's actually happening here? Here, the copper is leaving solution to form copper 2 plus. When it does that, it's losing those 2 electrons. Over here, the iron 3 plus is going to the going to platinum to gain its electron to form iron 2 plus. So the electron's available here, the electron is leaving here. Which salts am I using? I could use copper sulfate, I could use copper nitrate. Nitrates are a really good source, really easy to use. Sulfates are really common to use, doesn't really matter. What are my half reactions? I've got copper solid reacting to form copper 2 plus. And giving up 2 electrons. Whereas over here, I have iron 3 plus gaining an electron to form iron 2 plus. And remember, if they are ions, they are aqueous in solution. So at my anode, where oxidation occurs, always, it's negative for voltaic cell. I have copper 2 plus, I have copper, I apologize. Copper solid forming copper 2 plus and 2 electrons. At my cathode, where I have reduction, always, it just happens to be positively charged for voltaic or galvanic cells. I have iron 3 plus, aqueous, gaining 1 electron, forming Fe2 plus. Now my standard cell potentials here, again, we have to look these up, but copper solid being oxidized from copper 2 plus and 2 electrons has a cell potential of negative 0.34 volts. You may notice that it was positive in our last example, but we flipped the reaction around, so I flipped the sign on the cell potential around. I'm going the opposite direction now, so now it's going to be a negative 0.34 volts. And iron 3 plus gaining 1 electron, giving iron 2 plus, has a reduction potential of positive 0.77 volts. To add these together, I do need to always make sure my electrons are canceling. So I really need to have a 2 iron 3 plus, gaining 2 electrons to form 2 moles of iron 2 plus. When I add this up, so my electrons can cancel out. When I add this up overall, I get copper solid plus 2 moles of iron 3 plus aqueous, giving me 1 mole of copper 2 plus aqueous, and 2 moles of Fe2 plus aqueous. And then my cell potential, I just add up as written. Negative 0.34 plus 0.77 is going to give me 0.43 volts. So the one thing I haven't done yet is I haven't written the electrochemical shorthand. The reason I didn't do it is because I wanted to write out that cell reaction first, because the overall reaction is a great way for me to find my cell notation, because it's pretty much giving it to me the way it's written. This solid species here is my anode. Cell notation is always written anode to cathode, just like electrons travel. Electrons travel anode to cathode. I write my cell notation anode to cathode as well. So I've got my copper solid. Try to write that a little cleaner for you guys. I'm going to move this up just a bit. I apologize. I've got my copper solid. And in solution, I've got copper 2+. I need to put a phase diagram in here, or a phase boundary, I apologize, a phase boundary in here to separate out the copper solid from the copper aqueous. And I did not specify concentration, so I'm just going to say 1 molar for ease. That represents my salt bridge. Now, I've got 2 different species of iron in here, but they're both in the aqueous phase, which means I can write them next to each other. Fe3+ aqueous, Fe2+ aqueous. Phase boundary. I can't just leave things aqueous though. Your cell notation is kind of like a sandwich where you got the solid pieces holding the liquid in together. I've got to write down platinum solid. Now this is going to throw students off, but the platinum solid is the solid on the cathode side. I have to emphasize what solid I have there. So I'm going to write platinum and solid because again, it's kind of like a sandwich. I got to sandwich the liquids and the gases inside the solid phases. And then if I wanted to write concentrations in here, I could write 1 molar for each one as well. But again, if you don't write concentration, it's implied that it's a 1 molar solution. Draw the galvanic cell that is formed when a standard copper 2+ half cell is electrically connected to a standard hydrogen electrode. What is a standard hydrogen electrode? We're going to soon talk about the standard table of reduction potentials. And what we find is that everything has been measured against, well, a standard. And the standard is called a standard hydrogen electrode, or SHE. We call it SHE. We don't say she. We call it an SHE, standard hydrogen electrode. And so every potential has been measured against this to normalize them to one another. We don't often use a standard hydrogen electrode. They're just they're more work to use than not. So we do have other standards we can use, but everything has been measured to the hydrogen electrode. And so what I've got drawn here, this is showing just zinc with hydrogen, but it's the same kind of system. Okay, let me go ahead and draw what it would look like for hydrogen versus copper. And again, you can also see here's a picture of the hydrogen electrode as well. We've got a piece of platinum wire in here, and we bubble hydrogen gas through here. And the hydrogen gas will either be reduced or oxidized, depending on what I'm doing in solution. The solution itself, we can see down here, H+, it just means it's an acidic solution. So we're just going to use some kind of acid with a spectator that is not going to react. So like hydrochloric acid, sulfuric acid, nitric acid, something that's going to have a spectator ion that's not going to react in the system. If I was to draw this one out, got my 2 beakers, got my salt bridge, so my salt bridge, I'm connecting these through my voltmeter. Now, this one is telling me hydrogen and copper. This time, my hydrogen is going to be on this side. I'm going to have that piece of platinum in here and my hydrogen bubbling through this electrode. So it's going to have hydrogen gas bubbling through here. Again, this is my anode, oxidation, and a negative charge because it's a voltaic cell. Over here I will have my copper. So in solution, I'll have copper 2+. Because the system does tell me copper 2+. Here I will have hydrogen ions, or hydronium ion, H+ in solution. This is my cathode. Reduction. Positive charge. Electrons always traveling from anode to cathode. Let's see, I've got the salt bridge labeled hydrogen gas. Unless otherwise specified, you assume 1 atmosphere. That's standard conditions. So here at my anode, I've got H2 gas being oxidized two H plus ions and electrons. And at my cathode, I've got copper 2 plus ions, gaining 2 electrons and being reduced to copper solid. If I want to write out those two reactions, my overall reactions here, H2 gas, giving me 2H plus aqueous, plus 2 electrons. My standard cell potential here is 0 volts because, again, everything has been normalized to hydrogen, so we set that as the value of 0. And my copper, 2 plus my 2 electrons, giving me copper solid. And the cell potential as written here is positive 0.34 volts. Overall, I have H2 gas plus Cu2 plus aqueous, giving me 2 moles of H plus aqueous and copper solid. And my cell potential here for this reaction is positive 0.34 volts. How do I write the shorthand here? Now, again, I need to write anode to cathode. So my anode has that hydrogen gas. I'm going to assume 1 atmosphere because that is standard conditions. I also have H plus at my anode. I have to write a line for a phase separation because those are in different phases. Aqueous phase and gas phase are not the same. I'm going to assume standard conditions, so 1 molar. My salt bridge, but I can't just have a gas, right? I got to have a solid to sandwich it in. I've got to emphasize that I have platinum solid on that side. So that is my anode portion. I still need to write the cathode portion. I'm just running out of space. Copper 2 plus aqueous. I'm going to say 1 molar. Again, if you don't write a concentration, you are implying 1 molar. And copper solid. So we've now drawn them we've now talked about abbreviation for copper and zinc, but we've drawn it for copper and zinc up here. We've drawn it for copper and Fe2 plus Fe3 plus here, and we've drawn it for copper and hydrogen here. And we see that the copper slip in sides, right? The 3 galvanic cells that we've drawn illustrate the principle there's a hierarchy of oxidizing agents. What is your oxidizing agent? An oxidizing agent is something that oxidizes something else. It is reduced itself. We saw from these 3 examples that Fe3 plus oxidized copper, while copper 2 plus oxidized the hydrogen gas. Copper 2 plus also oxidized zinc. But because of that, we should be able to predict that the Fe3 plus would oxidize the H2 gas, right? If copper is able to oxidize hydrogen gas, but iron is able to oxidize copper, then it's fair to say that iron 3 plus, specifically iron 3 plus, I apologize for that, iron 3 plus should be able to then oxidize hydrogen gas. And what we have is the standard reduction potential table. Now, you can look these up in the back of your book. You're going to find more inclusive ones. The values are not going to change. They are standard. They are standardized to the standard hydrogen electrode. But these tables give us a lot of information. First of all, they give me my standard cell potential, which is nice. I don't have to, I can just quickly look up these numbers. So these numbers have been giving you this 0.34, 0.76, 0. The number, I forgot what the number is, but the number for iron 3 plus to iron 2 plus, all of that came from this table. But also, this gives me a lot of information about the strength of these species when it comes to oxidizing or reducing. What I see is, when I look at these numbers here, right, they're really positive at the top, they're really negative at the bottom. As I go down the table, From positive to negative, I'm increasing the strength of the reducing agent. What does that mean? It means they want to be oxidized. They want to lose electrons. Let's look at the species here and say, does that make sense? The top of the table, I have fluorine. The bottom of the table, I have lithium. Does it make sense to you that lithium would rather lose electrons than fluorine? Because it makes sense to me, right? Lithium is a metal, and it's an alkaline metal. It wants to lose one electron, just be like a noble gas. Fluorine doesn't want to lose electrons, it wants to gain them. So in that sense, the table makes sense to me. Yeah, I absolutely believe that the more negative the number, they want to be oxidized. They want to lose electrons. As I go up the table, I see the opposite effect. Going from more negative to more positive numbers is a stronger oxidizing agent. Remember, an oxidizing agent wants to be reduced. Meaning it wants to gain electrons. So same kind of concept. Does it make sense to you that fluorine would rather gain an electron than lithium? Because it certainly makes sense to me. The hierarchy here, though, is going to tell me which species is going to oxidize, which one is going to reduce, based on these values here. So there's a huge number of experiments that were performed to actually calculate out these values. But through all of these experiments completed, they were able to develop the standard hydrogen potential table. We do see here that the units here is a volt. It's been a while since we talked about volts, but I need you to remember that 1 volt is 1 joule per coulomb. So that is its unit of measurement. A coulomb is the unit of electrical charge. We talked about that way back in the very beginning of Chem 1, so it's probably been a while. We are talking about voltage here. So some things to think about. First, every half reaction in that table, you may not have noticed, was written as a reduction reaction. Everything was written with the species gaining electrons. If I look back up here, I can see plus electrons everywhere, right? This is the standard way to write these reactions. We always write them as a reduction reaction. We call it your standard reduction potentials for a reason. We are writing every single reaction as a reduction. To obtain the oxidation half reaction, we just reverse the equation. And that's what I've been doing in the examples above. That's why we saw copper flip back and forth between positive 0.34 volts to negative 0.34 volts, and then back to positive 0.34 volts. When I flip the reaction around, I flip the sign on the cell potential as well. So let's think about some things here. Which half cell was used as the reference electrode? The one that's set to 0. We call it a standard hydrogen electrode. Other things to think about. The more positive the reduction potential, the more the substance on the left-hand side of the arrow, meaning reactant side, wants to be reduced, meaning it's the stronger oxidizing agent. The more negative that reduction potential, the more the substance on the right-hand side of the arrow, so your product, wants to be oxidized, i.e., the stronger reducing agent. So let's put this table to use. Looking at this, what is the strongest oxidizing agent shown? What does oxidizing agent mean? Oxidizing agent means it wants to be reduced. Who wants that electron the most? Who has the strongest cell potential? Ag plus, not Ag. Right? The strongest oxidizing agent is whoever's willing to pay me the most in cell potential for an electron. Silver's willing to pay me the most. I look at these voltages like a payment. It is a payment of potential energy. How much is it willing to pay for it? Silver is willing to pay the biggest amount, 0.80 volts. But it's silver ion specifically, not silver. Just pure silver metal has an oxidation state of 0. It can't gain any electrons. The silver ion can. The silver ion is the most willing to, is the strongest oxidizing agent. It wants to reduce the most. What is the strongest reducing agent shown on the table? I'm going to look for the most negative number. Reducing agent wants to be oxidized. Be careful here. I see the negative 0.271. Now, again, this is on this table. If we look at the table before that had more values, we'd get a different answer here, okay? I'm talking about just this table here, just comparing a small set of numbers. If I look here, that negative 0.271 is the strongest reducing agent. It wants the electrons the least. It is the most willing to give up the electrons. But you have to be careful here. I want you to think about this. This is aluminum, not Al3+. Al3+ isn't going to give up any more electrons unless you really force it to. It doesn't want to. But the aluminum is the most willing to give up those 3 electrons. The easiest way to use the table of reduction potential is to set up a horizontal diagram. You are not required to do this, but I personally find it to be the easiest way to think about this. So let's go ahead and see what I mean by that. Describe the zinc copper cell using a horizontal diagram. Okay, what I'm going to do is I'm going to write out a number line. And I'm going to put my species on here. So let's find zinc and copper. Here's my copper, and my zinc is down here. I'm going to think of this like a regular number line, where I've got the more negative potential, negative 0.76 volts, here, and the more positive potential, positive 0.34 volts, here. They may both be negative, they may both be positive, one may be negative and one may be positive. I'm always going to put the more negative number to the left, the more positive number to the right. This is my zinc 2+ zinc. This is my copper 2+ copper. The electrons will still travel. It will always be anode and oxidation, cathode, and reduction. So it's just like when we drew out the beakers, but it makes it a little bit easier to see because I'm just using a number line now. Anode, negative, cathode, positive charges when we're doing voltaic cells. Now, I can quickly see what is the cell potential of this battery because I'm just looking at the difference between these two numbers. To travel from negative 0.76 to positive 34 volts, it is a difference of 1.10 volts. So the overall cell potential for this system is 1.10 volts. I'm going to shrink that down quick and show you guys, write out the reaction for you guys just for review and write out the shorthand notation so we can kind of, again, pull all of this back together. So what this is representing is zinc solid reacting with copper 2+ aqueous, giving me zinc 2+ aqueous plus copper solid. And if I want to, and the cell potential here, 1.10 volts. And now I can easily write out my shorthand notation as well. Remember, it's always anode to cathode. And the way I wrote my reaction is very intentional. I wrote it showing my solids on the outside so that I had quickly already almost written my shorthand notation. I've got my zinc solid. Then I'm going to put my anode electrolyte, which is my zinc aqueous phase, my salt bridge, my cathode aqueous phase, which is my copper 2+, my phase boundary, and my solid cathode, my copper solid. Again, since I did not put them in there, I'm assuming 1 molar concentration. If I wanted something other than 1 molar, if I had a solution that was not 1 molar, I would write those concentrations in here as well. So let's say that I'm using a 0.5 molar solution. I would say 0.500 molar, or however many sig figs I need. And I would do the same thing here. 0.500 molar. And now my cell notation is complete as well. What about if I have a nickel 2 plus half cell connected to a standard zinc 2 plus half cell? I'm going to do the same thing. Draw my number line. And now I'm going to find my two species. I've already got zinc. I'm going to go ahead and highlight the nickel. Now I see the nickel is negative, but it's still more positive than the zinc. So I'm still going to put the zinc here, negative 0.76 volts. For zinc 2 plus, zinc. And for the nickel, negative 0.23 volts, nickel 2 plus, nickel. The electrons still flow this direction. This is still my anode where oxidation occurs. And if I was applying the cell potential here, this hooks up to the negative terminal. If we think about the batteries being a plus size and positive and negative terminals on the battery, that's what I mean by that. The anode is the negative terminal. Cathode, reduction, positive terminal. Now the cell potential difference between these two is 4, can't read my own writing, 43 volts. So again, not asked for, but just for some extra practice, if I was to write out the reactions in this shorthand here, reactions would be zinc solid plus nickel 2 plus aqueous, giving me zinc 2 plus aqueous plus nickel solid. And my shorthand would be zinc solid, phase boundary, zinc 2 plus aqueous, my electrolyte of my anode. Let's just make it 0.25 molar this time. Why not? Let's change it up. Salt bridge, nickel 2 plus aqueous. They do not have to be the same concentration, so let's do 0.5 molar here. And nickel solid. So your anode and cathode do not have to have the same concentration either. They can be different phases or different concentrations. How do we apply this? Suppose a standard copper 2 plus half cell is connected to a standard iron 2 plus iron 3 plus half cell. There should be a dash in there. Describe the cell using a horizontal diagram. Got my diagram? Let's go ahead and find our species. We've got copper 2 plus, and we've got iron 3 plus, iron 2 plus. Where did I put you? And you're not on my list because I've got iron 3 plus to iron 3, or iron here, and I've got iron 2 plus to iron here, but those are not the correct reactions. I'm actually missing the reaction I need. So at some point I shall fix that, but not right now. Let's see, what is this potential? 0.77. So iron 3 plus 1 electron, giving me iron 2 plus, has a cell potential of positive 0.77 volts. I apologize. I'll try to remember to fix that. But that is what was missing from the table. Now, comparing these two again, I'm going to go ahead and draw out what do I know. I'm going to look at those two numbers, and I see that my copper 2 plus has a more negative number than my iron. Because again, these irons are not useful to me, right? That's iron 3 plus gaining 3 electrons going to iron solid, iron 2 plus gaining 2 electrons going to iron solid. That is not helpful. I need to compare this system where it's iron 3 plus gaining 1 electron. So I'm going to write my copper 2 plus. I apologize. I'm so used to writing on the board and having space. And then iron 3 plus, iron 2 plus here. My copper has a cell potential of 0.34 volts. My iron is 0.77 volts. And my copper is my anode, where oxidation occurs. And again, this is the negative terminal in a galvanic cell. My iron is my cathode. where reduction occurs. And a galvanic cell or voltaic cell, whatever you want to call it, this is the positive side. And the electrons always travel anode to cathode. The cell potential difference here, 0.77 minus 0.34 gives me, 0.43. I apologize, I was reading the wrong thing earlier. If you're wondering where the heck I got this number, it's because this one was wrong. And I shouldn't do math that fast. I should just do off the top of my head instead of trusting my notes. I apologize. The difference here you actually need to fix is 0.53 volts. I apologize for that. I was reading the wrong part of my notes. So 0.53 is the cell potential there. Back to this one. 0.43 is the cell potential here. So what is a cell notation that represents a system? First, I'm going to draw the reaction because for me, it's just easier to see the reaction. Plus, I like being able to connect it all and then think about what the diagrams would look like with the beakers, etc. In this system, I would have copper solid reacting with iron 3 plus, forming iron 2 plus. Remember, ions are aqueous phase, and copper 2 plus. Now, the copper has lost 2 electrons. I can do this by the half reactions if I need to, but I want to try to speed this process along for you guys so that you guys, well, the video long, but also that you guys can start thinking about it and seeing it faster. The copper is losing 2 electrons. The iron is only gaining 1 electron. This reaction needs to be balanced. So if you're unsure, go ahead and go back to where I balanced them as individual reactions a few slides ago. But otherwise, I want you to start recognizing quickly, since the copper is losing 2 electrons, I have to account for those 2 electrons in this reaction as well. Meaning I have to have 2 moles of iron 3 plus being reduced down to 2 moles of iron 2 plus. Because the iron is only gaining 1 electron, it's going to take twice as much iron as it does to copper. And then I'm going to write my overall cell notation. Got my copper solid. My copper is my anode, and that's going to be written first. Phase boundary, copper 2 plus, aqueous. Let's go ahead and say this one is 1 molar. Salt bridge. I've got the iron here. Iron 3 plus, aqueous. Let's say that's 1 molar as well. Comma, Fe2 plus, aqueous, 1 molar. And I may have run out of room, but I did not actually finish yet. So 1 second. And phase boundary. I've got to have something solid holding this sandwich together. And I'm going to use platinum because platinum is inert. Again, this is the overall reaction. And if I want to write the cell potential with it, then standard cell potential for this reaction is positive 0.43 volts. Let me shrink that down just a little bit so we can see that as well. And back down. And I realize we covered a lot in this module. I hope it makes sense, but what I would recommend practicing is try to write out the line diagram. Try to look up the values on the cell potential on the tables. Figure out what the difference in the cell potential is for that reaction. Draw out your half reactions. Figure out your total redox reaction. See how that correlates to the shorthand notation and see if you can draw the diagram with it. Identify when you need to use an inert material such as platinum or when you're just going to use the metal species that's in the reaction itself. Start identifying anode and cathodes. Okay, again, that goes to who wants to be oxidized, who wants to be reduced. Anode is always oxidation. The species at the anode is always being oxidized. The species at the cathode is always being reduced. In a voltaic cell, your anode will have a negative charge and your cathode will have a positive charge. So the terminals, the positive and negative terminal, when you're looking at a voltaic or galvanic cell, anode is always negative, cathode is always positive.